Thank you everyone for attending this webinar. My name is Vikram and I work for GL Communications. I am joined on this webinar with my senior engineer Bhavya. She is actually working out of our India office and I am working out of our Washington DC office. And today we are very excited today to talk about our 5G wireless lab testing solutions. So we do a lot in the 5G space, and myself and Bhavya will dive deep into it. So let's go ahead and get started. I think I see a lot of the attendees, and I recognize a lot of you. So I think you are familiar with GL Communications. But if you are not, we are headquartered in Gaithersburg, Maryland, just north of Washington, D.C. We've been around for over 35 plus years. We are a telecommunications consulting company, and we also manufacture test and measurement equipment. When I say test and measurement equipment, we make equipment for testing all different types of telecommunications networks. Everything from analog, public switch telephone networks, all the way up to high-speed Ethernet, 100 gig Ethernet, wireless networks, 5G, 4G, 3G, and so forth. We do a lot of land mobile radio testing. We do sonnet testing as well. So basically every different type of telecommunications network out there, we have test and measurement equipment that can test these networks, verify the performance of these networks, I help identify and troubleshoot problems over these networks. Our solutions include analysis, analyzing live traffic that's traversing these networks. We can also do emulation. We can generate all sorts of different traffic flows over these networks. We can visualize the traffic. We can do long-term capture and storage of the traffic, protocol decodes, and so forth. So we have a lot of different solutions, so please feel free to contact us at any time to discuss your specific requirements. So today, I promise Bhavya will do most of the talking, not me. She is our expert on 5G. But I'll just talk a little bit about our overall 5G solutions. We do both emulation and monitoring of 5G networks. So you can divide our solutions into two categories, emulation and monitoring. For emulation, we can generate all sorts of different 5G core network protocols. We can emulate different 5G core network interfaces. We can do load testing. We can send calls across. We can do signaling. We can do user traffic. We can do all sorts of different types of stuff. The emulation solution we also have interoperability with 4G and so forth, so we can do a lot of 4G testing and see how in non-standalone deployments how the 5G portion interacts with the 4G portion and so forth. We can do all of that type of stuff. Emulation is very important because you want to know how your applications perform when exposed to certain traffic flows. How does your infrastructure behave when exposed to valid protocol messages or invalid protocol messages and things like that? How does your network behave when subject to a large load, thousands, tens of thousands, hundreds of thousands of calls or gigabits of traffic going across? So emulation is very important for really understanding how your network behaves, how your applications behave in a controlled manner. Monitoring solutions, we also can monitor live traffic. So instead of generating the traffic, we monitor the existing traffic taking place over the network. For monitoring, we can decode all of the 5G protocols, all of the interfaces. We can deploy our solution anywhere in the 5G core network and capture traffic. We'll talk about it more, but basically you just hook it up to a monitor port or a mirror port on a switch, capture all the traffic, and our software will intelligently decode everything, build call detail records, classify all the traffic, compute metrics like packet loss and voice quality and things like that. So monitoring is very good when you're talking about live networks and you want to troubleshoot actual traffic going across your network and try to see what's going on, if anything's malfunctioning, where's the issue, and so forth. So please feel free to ask us about either one, emulation or monitoring or both. They can work in tandem too, so we can monitor the traffic that we are emulating as well. So we could be emulating traffic to your device under test and then also monitoring both traffic flows, the traffic to your device and the traffic coming from your device. So it all works in tandem. It's all actually controlled by one or two very simple to use user interfaces. So it's all very easy to use, and you don't have to bounce around between different interfaces. It's all very convenient. So many of you on this call are familiar with our message automation and protocol simulation test suite. That's a mouthful, so we abbreviate it as MAPS. MAPS is this common framework that can emulate a wide range of telecommunications protocols. Everything from your analog protocols like FXO, FXS, we can do TDM, T1, E1, and all the protocols that traverse T1 and E1 like ISDN, SS7, and so forth. And then it can also do wireless, going all the way up to 5G, all the core network protocols that occur over 5G, 4G. Actually, this graphic here is just a subset of all the protocols that the MAPS program supports. So we license it per protocol. In most cases, sometimes we license it per protocol suite. But it's really basically the same user interface. So if you're trying to do SIP emulation and then you want to do some 5G emulation, it's actually the same interface. And you can, it's very easy to just kick off calls and various call scenarios and call flows and traffic flows, all from the same interface. It's all based on the underlying MAPS framework. Very easy to use. There's both a graphical user interface, but we also provide Python scripting and Java scripting capabilities with our MAPS program. So if you need to do really advanced stuff, you don't want to click buttons on a screen over and over again, you can write scripts, and we can write scripts for you. We can help you in terms of writing complex testing scenarios. So that's a little bit about the MAPS framework. Now let's talk about 5G in particular. So the 5G network, so you have a gNodeB out there, right? And that's a base station, and it's broadcasting wirelessly, transmitting and receiving to endpoint devices like cell phones. Now, once it hits that, once the traffic from the cell phones hits that gNodeB, it gets converted into wired traffic and sent across the core network. So the gNodeB does both wireless and wired communications. When we supply 5G solutions, we can supply you with a real gNodeB or an emulated gNodeB. If it's an emulated gNodeB, then we don't do any wireless aspects. We just emulate the user endpoints and the user endpoint traffic and all that stuff. It's just going to be a server-grade PC that's generating all the wired traffic into the core network. So we can do both ways. If you may be interested in the wireless aspect, but you may not be. You may just be interested in the wired core network aspect. So we can do real gNodeB or emulated gNodeB. For real gNodeB, we can supply you with different solutions which cover different frequency ranges in the 5G standards, and so that's all easily doable. Okay, so once it hits the core network, it's really all just packet based. So our MAPS program is just running on this Windows server PC or in a cloud instance, and it's generating packet flows. and it can simulate all of these different interfaces and generate traffic. So it can, wherever you see a GL icon, it can emulate that device. So the maps program can emulate the AMF, it can emulate the NSSF, the AUSF, and so on and so forth. So it can act as all of these different types of devices and generate traffic, receive traffic, and so forth, or monitor traffic. Now the core network is handling signaling as well as actual call flows and audio flows and data flows and things like that. So all of that is doable with the MAPS program. So this is a little bit about the overall 5G architecture. We can be anywhere here or everywhere. And then in your scenario, if you can test very specific things. Some customers are interested in only one specific interface that they need us to emulate, but some customers need a complete 5G lab. If you need a complete 5G lab, we can supply the complete 5G lab. It's very simple, actually. It's just the gNodeB and a server-grade PC running the MAP software. So it's a very simple deployment. So that's a little bit about how the 5G network looks like and where we can be in the 5G network. Okay, this is a lot of text on the screen right here. I apologize. You don't have to read it all. But basically, we have a very simple user interface, both a graphical user interface and a web-based interface to kick off the MAPS program and begin emulating traffic flows. I talked about all these different interfaces that we can emulate. We can do web traffic. We can do encrypted traffic, TLS, and so forth. We can generate valid and invalid messages to see how your devices are handling the traffic. We can do performance testing, functional testing, interoperability testing. We can emulate a large number of cell phones, like up to 60. With one server, we can emulate up to 64,000 simultaneous calls taking place over that 5G network. We can also emulate GTP traffic, up to 40 gigabits per second of GTP traffic. While this is all happening, we can also measure voice quality across the network using the latest algorithms, PESC, Polka, and so forth. And again, we support Python scripting as well. So let's go ahead and move on. At this point, I will turn it over to Bhavya, and she will talk more specifically about different use cases with our MAPS 5G emulation. Bhavya, feel free to go ahead.
Hello, everyone. Yeah, thank you, Vikram. Thanks for the insightful introduction for the GL and 5G emulation and monitoring solutions. So building on the great introduction as a foundation, so let's now explore how GL's emulation solution can help in testing various 5G elements. So I'll be discussing about certain use cases where our 5G emulation can be used. So the screen which you're looking at is the first use case which will come to our mind whenever we are discussing about the 5G emulation. So in this case, we are considering the entire 5G core as the device under test or the system under test. So by emulating gNodeB with the emulated UVs, so we can test all the functionality of the 5G core. So here we are saying emulated UVs and the emulated gNodeB. So this is without the real gNodeB, without the real UVs or the actual RAM. So our emulation starts from the N1, N2, and it covers all the N1, N2 features such as UV registration, deregistration, authentication, identity procedure, ciphering, video session management, UV context management, SMS over NAS, and even the N3 interface traffic such as VoNR call or the data browsing sessions, etc. So with this, all the functionality of the 5G core can be tested. Also, we can emulate thousands of emulated GNBs with the distributed UVs to test the load of the load capability of the 5G core. Yeah. Coming to the next one, this is the complete another set of feature here. So here we are just reversing the first case. So in this case, we are considering GNB as the DUT. So by emulating just AMF with the N1, N2, so we can test the complete functionality of the gNodeB in at the N1, N2 interface. Okay, so the same features which we mentioned at the N1, N2 interface, such as registration, ciphering, authentication, PD session management, SMS, N3 interface. So everything can be tested. So only the focus will be limited to N1, N2. So with the N1, N2 interface, we'll be testing the functionality of the gNodeB. So if at all you want to expose the complete 5G core elements, uh, the initial 5G architecture, so every 5G core elements will be used. So if only the GNB is under test and you are not interested in other 5G core elements, so we can use this configuration where only AMF at the N1, N2 can be used to test the GNB. So here AMF even can test gNodeB with PD session activation, deactivation, network initiated activation, deactivations. So and it can allocate IPv4 and IPv6 addresses, and it can also act as the gateway for the N3 traffic. And it can the browsing on the real UIs if is connected to gNodeB. So the browsing also can be done via our IMF, which also acts as the N3 gateway there. So coming into other use cases. So from this slide onwards, we'll be discussing almost the different use cases. So where we are considering each network element or network function and how that network function can alone be considered as a duty, and how the complete testing of the duty can happen with the GL emulation tool. So in this slide, we are seeing the AMF as the device under test. So how only the AMF can be isolated from rest of the elements. So on how we can wrap around the AMF and test the complete functionality of the AMF by emulating all the surrounding nodes or the network functions. So in this case, we can emulate, as mentioned in earlier slides. So we can act as the UVs and the gNodeB to emulate N1, N2 and test at the N1, N2 interface. Along with that, we can also emulate the service-based interfaces, that is N12, N8, N11, N20, and N17 interfaces to emulate different service-based procedures here. So this includes, if I summarize the functionality or procedures supported for EMF isolation testing, they are NG setup between the gNodeB and AMF, UA registration, identity, authentication, and security. And coming to the SBI interfaces, so it will be around like AMF registration and deregistration for the 3GPP access with the UDM, and authentication testing with the AUSF, and PDU session establishment and releasing using the N11 interface with the SMF. So SMS over NAS with the SMSF, and check IMEI with the EIR. So all kind of procedures can be tested by keeping EMF as the DUT. Similarly, we are discussing here about the UDM. So again, UDM is another important function at the 5G core. So which is responsible for managing all the subscription data of the UVs, as well as the data network information. So UDM manages data for accessing authorization of the user registration, and it also maintains the DNN profiles. So testing a UDM requires other network functions such as AUSF, AMF, SMF, and the SMSF. So by acting as different kinds of nodes, we can test UDM for registration of individual network functions. And here AMF, SMF, and SMSF registration for the 3GPP access via UDM, and user identification handling, subscriber data management, even empty SMS delivery support, and authorization and authentication support. So these kind of features can be tested. So whether UDM can handle all kinds of signaling in the N8, N13, N21, N10. So all these procedures can be tested by isolating the UDM with the different by emulating different network elements. Similarly, AUSF can be surrounded with the AMF and the UDM by emulating N12 and the N13 interfaces. So basically, these interfaces does the authentication. So AMF will request for the authentication. In turn, AUSF will look up to UDM to get the authentication vectors and does the authentication and um, provides the vectors to the AMF. And once the UE authentication is successful, so it reports back to the UDM about the successful or the unsuccessful authentication. So the N12 and N13 covers only the authentication to test the AUSF network function. So then comes the SMF isolation. So here SMF is a very critical and network function which manages the communication between the control plane as well as the user plane via the N4 interface and the N11 interface. So the SMF can be surrounded with AMF, UDM, and UPF to manage the communication between the control plane and the user plane. So AMF can be just generating the N11 without requiring UVs to trigger the registration procedures or the PDU session request. So AMF can individually or it can generate N11 directly. So the N11 registration or N11 PDU session requests can be triggered to the SMF. So SMF in turn can generate the N4 interface messages of the PFCP protocol to control the UPF. So UPF even can act as the even the traffic gateway, and it can terminate all the N4 traffic, and SMF can look up to the UDM to get the subscription data. And so SMF isolation can be tested by emulating AMF to trigger the session management request. So UPF for traffic flow emulation and UDM to provide the subscription details. So then comes the SMSF isolation. Here with the SMSF isolation, we can perform the SMS over NAS procedures. So here AMF as so SMSF can be surrounded with AMF and the UDM to emulate N20 and N21 interfaces. So where N20 is actually generating the SMS towards the SMSF. In turn, SMSF will look up to the UDM and get the information of the or the destination UE where the SMS has to be sent. Once it gets, so it sends back to the AMF the empty SMS. So the SMS will be terminated at the AMF itself. So thereby testing the functionality of the SMS, whether it can route the SMS to the destination UE. So the SMSF can be tested alone by acting as only the AMF and the UDM. So next, the UPF isolation. So here UPF stands for the user plane function. So it connects the UE to the data network, handling the encapsulation, decapsulation of the GTP for the user plane. So it is part of the CUPS or the control and user plane separation, enabling the packet processing and traffic aggregation to, as the it can act as a network edge. So here in this case, SMF GL can act as SMF to only emulate the N4 standalone N4 interface. So where N4 so SMF can generate the PCP association, setup, update or release procedures, and PDU session establishment, modification and release procedures. So multiple PDU session per UV can be requested, and it will be tested whether IPv4, IPv6 address assignments will be happening properly. So different kinds of addresses will be assigned and checked. So also the heartbeat procedure between the SMF and the UPF is also supported here. So the even the heartbeat procedure can be tested. Also, the SMF in the N4 interface can also generate the entry traffic without the need of the actual UV. So even the UPF as a gateway functionality can also be tested in the UPF isolation. So this is a simple and optional interface, that is the N5G EIR. So or the N17 interface where the EIR, 5G EIR comes into picture. So here AMF can trigger check IMEI request to the 5G EIR to get the IMEI status, whether it is whitelisted or blacklisted. So it can test whether EIR can respond to the valid UEs with the proper status, or how it will behave if an invalid UE is sent. So this kind of testing can be done with the EIR isolation. So this is the NRF isolation. So NRF also can be treated as a device under test, and it can be surrounded with all the network functions available in the 5G. So here NRF is the network repository function. It's a key standalone core network component, so that that can register different 5G core network functions such as AMF, UDM, AUSF, SMF, SMSF, AIR, etc. So it can register different NFs or network functions, and if any network function wishes to establish a connectivity with other network function, so it can query to the NRF to get the information about uh, the network function which actually which can actually serve the certain criteria which any the network function which wants to discover any other network function. So it can um, initiate request to the NRF to get the or discover the other NFs matching the criteria or specific criteria which I am just looking for to have the specific functionality for the UE. And even the NRF can track the status of the other instances. So in order to test that, so even we can support, we can do the subscription and the notification procedures. So the network functions can subscribe to the different NF and will request for the notification when any specific NFs matching any specific criteria is registered. So NRF can trigger the notification to the network function which has been subscribed for that network function. So even the subscription functionality can be tested with this NRF isolation. So also heartbeat is supported. So these are about the 5G use cases. So till this slide, we discussed about different 5G use cases where we are treating or testing individual network components separately, or isolating different network functions in the 5G core network. So in addition to that, we also have a the end-to-end emulation. So where the 5G end-to-end call flow can be generated. So in this slide, you can see this is the call flow snapshot which is taken from the AMF. So which is the key network function in the 5G architecture, which actually interacts with each and every 5G node, 5G network function towards the 5G core. So these slides are capturing the complete end-to-end call flow which GL emulates. So you can see the registration request generated from the gNodeB, and on reception of the registration request, so AMF requesting for the authentication vectors to the AUSF. So AUSF in turn looking up to the UDM to get the authentication data. So once it gets the authentication information, AUSF returns back to the AMF, and the gnode and AMF will send to the gnodeb. So once gnodeb relays the same to the UV and gets the authentication information, and then the same thing is followed. So it returns back to AMF, and AMF actually calculates the authentication and then sends to the AUSF, and AUSF again report the authentication event, whether it is successful or not to the UDM. So after that, the security procedures will take place. So you can see each and every transaction happening here. So each network function is currently it is with respect to AMF. So AMF is registering to the UDM for the 3GPP access for the AMF for data, for NSSCI and different several others. So it even registering for the SMF and the SMSF. So all the and also for the UV context. So it registers or it will get every information of the UV and then continues with the call flow. So in this here, you can see like once the uh, STM subscription data is downloaded from the UDM. So registration accept is being sent out. And after the registration complete, you can see the session establishment is happening for the user traffic or the VONR call. So that is happening between the this AMF will send the PDU session request to the SMF, and that SMF in turn interacts with the UDM to get the PDU session information of the UV, and then interacts with the UPF with the N4 interface to establish the actual user plane traffic sessions. So here, once the user plane traffic is the session is created, we are also modifying the session and deleting the session once the data browsing or the VONR call is completed. So once it is completed, even the sessions can be deleted, and that will be notified to the UDM. So once UV switches off or disconnects the data, so all the subscription information are deleted from the UDM. The session related information are deleted. So the current registration information are deleted, and the UV context is released once the UV is completely deregistered. So this is the end-to-end call flow. So if we emulate the end-to-end call flow, this can be very useful when this can be a useful input for the monitoring solution. So if anybody wants to develop any monitoring solution, so this can be a complete end-to-end calls, which can be a great input for the monitoring solutions. Also, this can be very useful in educational purposes because it covers most of the 5G elements or the 5G network functions and all its interactions within various interfaces, so that everything can be viewed within a single system or single, you can say, only software only solution. Whenever a very less number of UVs will be used. So it is a software only solution with a one box solution. So where everything can be deployed within a single system. So it is a very simple and a very portable solution. So till now, Vikram has introduced the MAPS framework. So till now, the MAPS framework was Windows only solution. So currently, we have enhanced our MAPS framework to uh, for a web interface. So currently, MAPS web interface can run on any of the web browsers. So thereby enabling this application can be run on the both Windows and the Linux OSs. So now we are extending support on the Linux as well. So the coming slides, we are just trying to introduce the maps framework and how the maps features have been brought into maps web interface. So this slide is the web dashboard. So here you can see the user can configure multiple test setups. So one single maps web dashboard, you can user can configure multiple test setups. Here, test setup can be something, for example, here you can say one setup is 5G lab. So if you want to control multiple test setups, so one can be 5G lab and one can be just N1 N2 emulation and one can be 4G lab. So different test setups can be configured and controlled from one place. So here, once you define a 5G once you define one test setup, so then you can see in each test setup you can add a desired number of nodes, so which you want to emulate in any of the test setup. For example, if your device under test is a 5G core emulator, so you can just choose like your gNodeB emulation is the only node in this test setup. Okay, so whenever you say add node here, so you can you'll be given access with the complete, you can select the technology, whether you want to emulate the 5G, 4G or the IMS, and then you can, the nodes will be listed within each technology. So for example, here 5G technology is selected and you are given the list of all the 5G nodes available. So once you select the node, so then what are the interfaces you want to emulate? So the all the individual interfaces are listed. So you can choose a single interface. So where if you want to have a gNodeB emulator, only N1 N2 will be visible. So because it can be only N1 N2 signaling. So if it is an AMF, so you'll be you'll get a list of all the interfaces where AMF can be a part of. So in this case, you can see N1, N2, N8, N11, N12, N17, N20, 22, and 51. So these interfaces are listed. So along with that, you can see one more multi-interface. So that is nothing but, so if you want to connect AMF to all other interfaces within the 5G core, so then the 5G multi-interface, this protocol or interface to be selected as multi-interface, and you can also select the release version. So currently we support release 15 and 17. So 17 is the latest. So all the 5G currently all the 5G NFs are updated to release 17 version. So you can select what kind of node you want to add. So adding nodes is nothing but you can define your setup. So how many nodes you want, or how many, what is the kind of node, what actually it emulates. So here, this example, we have considered it as a 5G entire lab as a test setup here. So currently we have configured most of the 5G network elements, network functions. So gNodeB, AUSF, SMF, UDM, AUSF, SMSF, AR, and UPF. So all these nodes we have configured with the management IP. Management IP is nothing but the IP of the system where it will be running, and that port is that is the IP and the port where the TCP connectivity between the web interface and the actual system where the application will be running, that will be configured here. So once these things are configured, you are connecting to you have to connect to the systems where the connections will happen. The connectivity between the actual systems where the application running and the web interface is REST based. So once the connectivity is established, so you can see they are turning green. So once the connectivity is established, so then comes the configuring individual interfaces or individual nodes or the network functions for the transport related information or the actual node related information. So in case of transport, you can see the where in case of gNodeB, so we have to input the IP address where the AMF is configured. So IP address of the AMF you have to configure, and what is the GDP IP of the gNodeB, and you can also configure the PLMN IDs or macro ENB ID, short macro GNB IDs. So actual the parameters which are necessary for a particular network function. So those things to be configured. So these configurations will be one time. So once it is done, so it will be saved until you change your test setup. So one time configuration is required. So these configurations are exposed via JSON files, but you have a GUI editor to change the values and configure them. So you can configure each and every function. So we are just showing one or two examples here. So you can configure all the nodes in this manner. So you can visualize everything and configure in the web interface. So once you configure everything, and you have to click on start all nodes. So once you start all nodes, the connectivity between all the nodes will be established, and you can check for the transport status tab. So where you can get this transport status of all the network functions, and what and all transports are up. So you can see the gNodeB SCTP association is up with the IP address. So this IP address is of the AMF. So at the AMF, you can see it is the connectivity, SCTP connectivity is up with the gNodeB, and also it has HTTP connectivity between the various nodes. So it is acting as a client to the UDM and this AUSF. So there are multiple client sessions and two server sessions are running at the AMF. So this is the transport status where you can get an information of all the nodes and the transport status. Once the all the nodes are properly established the transport communication, so then comes the profile editor where actually the UV configurations will be made again with the help of the JSON editor. So this is a JSON editor where you can configure multiple UVs. So even you can go for the JSON configuration where if you want to have a functionality kind of testing, it can be limited to around 500 to 1000 UVs. So where finer control over the individual parameters will be supported. So whenever the functionality testing is involved, it's better to use a profile editor where micro informations can be configured here. So all the information you can configure, and this will so each profile here will act as one UV. This is what we call it as emulated UV. So whenever you start the GNB and the calls within the GNB, so each application or each UI will start emulating the N1 N2 signaling by using the configurations made in this profile. We also have something called auto-generated UVs. So where you don't want these kind of all the parameters to be exposed to the user, only you're interested in simulating load. In that case, will allow you to configure the ranges of the EMC so that the sessions will be established even without configuring the profiles. So range of the starting MC and the ending MC, the number of MCs. So then using that, load can be emulated. So once the profile is set up, so this is the load generation screen. So where you can add the script, and you can mention what is the load you want to run. So there are different load patterns available. For example, step, fixed, uniform, ramp, normal, sawtooth, step, sawtooth, in order to simulate or emulate the real-time network loads scenarios. So different types of load is supported. So user can select any of the load and can select the desired profile, or he can go for again auto-generated UIs where we no need to worry about the profiles. So once you configure these things and say start, the Maps web interface starts emulating or sending out N1 and N2 sessions. Thereby, it triggers all the interactions between the 5G core elements. So we can see what is happening at the load using the statistics. So here the load gen 1. So load gen 1 currently 10,000 sessions active, and it can say how many are active, how many passed, how many completed, and what is the CPS at this time. So you can get the complete information of the load which has been generated. Also, you can get the statistics of or counters for each message types which are actually being exchanged between the different entities or the network functions. So you can get the different node statistics. So this will give you an glimpse like that the test is going on and whether all messages are successful or not. So those things will be available to you. So even the SMF message statistics where the PFCP message exchanger also can be seen. So here, because we have included two PDU sessions per UV, you can see we have placed 10,000 calls, but you can see the 20,000 session related messages here. We also have something called events and error logs. So this will give you any if any error or any unexpected signaling is happening at any of the core. So a core network element. So we are logging the errors and events. So this will help in debugging the scenarios. So um, coming to the preprocessors, we have two very important preprocessing tools for the maps web interface. So one is the message editor. This is almost similar to the message editor which is present in maps windows. So only thing is the same functionality is brought in the web interface. So here the user will be given access starting from the NGAP layer towards the complete information of the NGAP layer and the NAST layer will be allowed for the users to manipulate or change or create the variations of the messages, and that can be used in call flows. So n number of combinations can be possible, and user can create his own messages and even can tweak the scripts if he wants to emulate any kind of valid or invalid scenarios. Tweaking the message sequence or with a different or unexpected message sequence can be generated, and different message contents with different combinations of the information elements also can be created using message editor. So this YAML editor is the next is the YAML editor. It is exclusive to 5G. So here all the SPI interfaces are actually supplied with the YAML files with respect to individual interfaces. So which actually defines the contents of the individual operations using a JSON format. So we have come up with a YAML editor where a user can create a JSON message content. So without even looking at the YAML editor, we have provided a GUI for user interface. So there user can create a JSON message for all the SBI interfaces. So this is a very important and 5G exclusive feature in the Maps web interface.
Okay, thank you, Bhavya. Since we don't have too much time left, I'll quickly go through the rest of the slides. As I mentioned, we also offer Python scripting. So everything that you saw in the web-based interface can also be done through a Python script. This is very useful in situations where you don't want to constantly press buttons, start, stop, and you just want to have a script that automatically goes through a whole bunch of different scenarios for a certain period of time. Scripting is always a better option. So we support Python scripting. It doesn't even have to be on the same PC as the Maps software. The Maps software can run as like a server, and then the Python script can be executed elsewhere on the local area network on any other Linux or Windows PC, and directly talk to that Maps server and execute commands and so forth. So this is just a really quick snapshot of our Python scripts. Don't worry, we provide a bunch of sample scripts, and we can also help you in writing your scripts, or we can write the scripts for you. It's all pretty easy, straightforward to use. Okay, so just really quickly, I also mentioned monitoring. We can monitor the whole 5G network simply by connecting into a monitor port on a switch and grabbing all the traffic. So the PacketScan software is perfect. I mean, it's very nice because you can deploy it on a Windows PC. Just hook it up to a monitor port on the switch. It can decode all the protocols in the 5G network, and so forth. So PacketScan is a very powerful protocol analysis software. It gives you full decodes of all the packets captured. It can build call detail records. It can trigger alerts and actions and follow-on actions. It can save calls. It can do a whole bunch of different things. It can show you the ladder diagrams for all the calls and all the call flows, and much more. So PacketScan is very nice. It's also, if you need to capture a high volume of traffic, like maybe multiple gigabits per second, 10 gigabits, 25 gig, 40 gig, 100 gig, we have hardware appliances with our PacketScan software, which can capture all of the traffic and do all the decoding without any packet loss, and save the packet captures as a PCAP file or our own proprietary file format, and so forth. So the PacketScan software is very, very versatile for monitoring 5G and all the other telephony protocols that I mentioned at the beginning of this webinar. So please let us know if you are interested in monitoring. Then we can talk more about PacketScan. Okay, yeah, thank you everybody for attending the webinar today. For more information, if you have any specific questions, please feel free to email us at info@gl.com. Thank you, and have a good rest of your day or night, or wherever you're dialing in from. Please enjoy the rest of your day. Thank you.